Good evening, my 11th standard warriors. Today it's time to float and also question how do ships, which are so heavy, stay afloat without toppling over. All of this, buoyancy and flotation with me, your favorite Captain Shreyas, your physics master teacher at Vedantu, going live. Welcome aboard to Enthuse. Let me give you a brief roundup of what we are going to do today. This is lecture number 2 of fluid mechanics. I hope you have watched the lecture number 1, and in case you haven't, you need to first of all hit the subscribe button and make sure you go back to the previous class and check out all the important things about hydrostatics, barometer, manometer, and how pressure varies and what's pressure gradient and all of that. So anyways, let's continue, and in today's class we're going to talk about buoyant force or the upthrust force. Then we are also going to talk about the Archimedes principle, how things float, and different problems on all these topics along with center of buoyancy and toppling. So an amazing session right up for all of you. So do not forget to hit the subscribe button and smash the like button, and thank you so much for all the support and all the love that you have already showered. Welcome aboard all my lovely warriors. How is everyone? Is everyone good? Is everyone doing well? Hi Shubham, hi Madhav, Ishpreet, Idea Student, Saja, welcome Dakshin. Good evening. Good evening. So done with your snacks, done with your playtime. How is it going? Do you have your term examinations that are going on? And if your term examinations going on and you're still here, I'm really proud of you. That means you're very dedicated towards JEE. Welcome aboard. And those of you who have completed your term 1 examinations, well, that's good. I mean, now is the time to continue our journey towards term 2, and eventually we have to crack JEE 2023. Even if you are a 12th standard student, you are still open. You can still watch this class like a revision. Great going. Hi Akash. Looks like everything is going good. Vivek, very good. Thank you Ishpreet for all the hearts. Chalo, let's begin with the session. Hi Aditya. Thank you Jaffin for all the love. And now we're going to talk about fluids and solids together, meaning the solids will try to immerse themselves in the liquid, and we're going to see what effects happen. Many of you might have heard about Archimedes principle and the famous story where he was, that's what the legend says, where he was just in his bathtub, and then he suddenly realized that, oh, I'm feeling light, I am feeling very, weightless. So there must be a reason for that. And yes, there was some water which came out of the bathtub, and that's when he realized, okay, there is some water which gets displaced just because I'm sinking or I'm immersed in it. And yes, there is some kind of force which is helping me reduce my weight, and that's what he called as the buoyant force or the upthrust force. And then he was so happy that he ran around the town naked. Thank God we don't have him right now out here. All right. Now, what is the first principle? The first part of Archimedes is all about how much liquid gets thrown out, how much liquid gets, displaced. So we talk about displaced fluid out here. And this is one common experiment. You would have done this back in your school days, where you had to find unknown objects, volume. Some random object's volume needs to be found. So what do? You take a beaker or you take a test tube, and then there are markings on it. You pour some liquid, see what's the reading. Then you drop that unknown solid in that. So you will see the level comes up. So the difference of them gives you the volume. Correct? So that's what the first principle is all about. If you see, this is the increase in the height. This is called as the displaced. This is called as the displaced fluid. Everything when immersed in liquid, when submerged in liquid, it will throw out. It will, take the place of the liquid. Hence that liquid has to give away. So it's something like this. It makes sense. If this is your liquid, and if the solid comes over here, this much amount of liquid has to come up. So that becomes your displaced fluid. I have a very easy question for you. Are you displacing any fluid right now, wherever you're watching this lecture from? What do you think? Are you immersed in some kind of a liquid? Thank you, Sakshi. Are you guys immersed in some kind of a liquid? Hi, Motivator. Hi, Mani. Welcome aboard. Hi, Dhirengar Aljlu. Welcome aboard, my warriors. Motivator says no. Vivek says no. Okay. Well, yes, Vivek, you got it right. Air is also a fluid. So technically, all the Pandus, all you Pandus are immersed in the ocean of air. Think of it like this, that this is the atmosphere, this is the topmost layer where the ionosphere is. You are immersed in the ocean of the air. Yes, just like if this Pandu looks at a fish, the fish is submerged. The fish is submerged in liquid, you are submerged in air. So technically even you are displacing some fluid. Do you guys agree with this? Do you guys agree with this? I'm pretty sure many of you wouldn't have thought about human beings or things on land this way. A very interesting way to look at it. So lots of fascinating things coming up. Let's move ahead. Now, the first law, everybody is clear that whatever solid is there, whenever it is immersed, it will displace some liquid. You can see that it takes over that space and it displaces that liquid, and this now is going to give rise to a very interesting thing, and that is the second part of the Archimedes principle, where we are going to talk about forces. So Archimedes thought that when any solid is immersed in kind of a liquid, you can see that this is the part of Archimedes. We cannot show it because this is a channel for kids, all right? So this part is censored, guys, it's all right. So when Archimedes was inside, you can see this much part of that solid got displaced and he felt lighter, and that means there was a force acting on him, which was not your weight, spring force, nothing. There was a new kind of force which came into effect. And that force which made him feel light, which pushed him upwards, is called as the upthrust force, is called as the buoyant force. Everybody getting it? The force, yes, the force which was acting on that solid, which was acting on Archimedes, which is going to act on any solid which is immersed in liquid, that is called as the buoyant force or upthrust force by the liquid. That's what it is. Very good. Hello Saja, hello Ramya, join in. Now, what is the value of this buoyant force and how does this buoyant force come into play? Let's figure this out. Vivek, we have an amazing content team which makes this amazing content just for you. So a big round of applause and go smash the like button for our amazing content team who gives us all these amazing content. Now, here is my logic. Observe this. Just imagine this is your liquid. Okay, this is your liquid, and let's say in this liquid you hypothetically consider a system of the liquid, and let's say the system of the liquid is this one. Okay, this is the system of liquid. So this is a system of that particular liquid or fluid, whatever it is. Now, if I ask you, draw the free body diagram of this particular liquid which is enclosed in this green space, the answer is very easy. All you need to think about, what are the different forces? One is the own weight of this liquid. Agreed? The own weight of the liquid will act downwards. So I'm just going to put an arrow mark this way. So this is going to be nothing but the weight of this particular liquid in this particular space. Which space am I talking about? I'm talking about this space right over here, which is now enclosed, and it's a part of some hypothetical system. What I'm trying to do right now is the derivation of buoyant force. Observe neatly, because if you lose track, then I will have great time, a big difficulty explaining it to you again. So please observe this carefully. Now, apart from this force, there must be one other force which should balance this. Because think about it this way. This is a hydrostatic fluid. Which chapter are we studying? Hydrostatics. So in hydrostatic fluid, static means it is stationary. Therefore, the net force must be 0, net torque must be 0. We have all seen this. There must be one more force to balance it. Where is this force going to come from? Here is the answer. Remember, at any depth you have pressure force, the force due to the pressure, hydrostatic pressure, the weight of the liquid column. Do you remember it? Do you remember this? Yes. So there will be hydrostatic forces everywhere. Here the pressure is less. Remember, the force due to the pressure is always perpendicular to the area. So perpendicular to the area, there will be a force here. Perpendicular to the area, there will be a force here. As you go down, the pressure will increase. So will the force. So will the length of the arrows. So as I come down, I should show little bit longer arrows. I hope you agree with this. So the arrows become longer because they are going to be of higher pressure and they will be always perpendicular to the forces. This is how it's going to look like. Now, if you look at these arrows, what are these arrows? These are basically pressure multiplied by area, which is nothing but, these are nothing but forces due to hydrostatic pressure. Now, if I ask you, do you think all these forces, the red arrow marks, will cancel each other? What do you guys say? Think about it. Hi NV18, hi Manjunath, hello, welcome aboard. Think, will all these forces cancel each other? Think carefully. The length of the arrow marks are very important. I know all the forces are there from all the sides, but the arrow marks which are pointing down are smaller in length. All the arrow marks which are pointing down are smaller in length, but all the arrow marks pointing up, look at these arrow marks which are pointing up, they are larger in length. So where will the net force be? The net force will be upwards. Exactly, IT aspirant. Think about it. Prakash, it will not cancel. Very good, Prakash. Excellent. Yes, Thalu, I'll start it this week only. Concentrate now. So essentially the idea is these forces do not cancel out. So they will have a resultant force. That resultant force, the resultant of all basically the hydrostatic pressure forces. This is basically called as the buoyant force. What is it called? This is called as the buoyant or upthrust force. That's what you call it. It's the resultant of all of them. So the resultant of all of them must cancel out this and it will be upwards exactly this way. So this is your buoyant force, FB. I hope this is making sense. Now, here is my idea. The idea is, imagine if you take any liquid and you actually have some kind of a solid of, imagine the same shape, something like this. Imagine you have a solid of some shape like this. It has displaced some fluid. It has displaced some fluid around it. It has thrown away, and around it there will be pressure forces due to hydrostatic pressure. There will be forces like this, and the arrow marks down will be much longer in length as compared to the arrow marks from the top. These forces from all the sides will have a resultant force. They will have a resultant force that is called as the buoyant force. How do you find the buoyant force? Very simple. Again, I am repeating. How do you find the resultant of all these PDA, pressure into area, the resultant of that? In this volume of solid, just imagine a liquid. In this volume of solid, I am repeating, imagine a liquid. That liquid will experience the same forces from outside as that of the solid. Makes sense? Because at this point, there will be same pressure as that at this point. If I take the same shape, same size, whatever forces, whatever arrow marks I am drawing over here, the same arrow marks should come over here. If these arrow marks produce this resultant here, these arrow marks for the same shape should produce the same resultant over here. So do you agree? Whatever is inside really doesn't matter. What matters is the shape and the size. What matters is basically the shape and the size. So essentially what has happened, the resultant will be same as that of, the scenario when there is water inside. And now just to figure out what is the value of this buoyant force, what is the logic I have used? Since both the resultants are same and I know this resultant is equal to the weight of the liquid, hence I know this buoyant force must be equal to the weight of the liquid. This is the weight of the liquid which has been displaced. You have put the solid and you have replaced the liquid with this solid. So it is exactly equal to the weight of the liquid which has been displaced. That's what has happened. I hope this is clear. One last time I'll repeat. This solid, when immersed in the liquid, it displaces some fluid. So if you take away that liquid, you have put this solid inside, there will be forces from everywhere, they will produce a resultant. To find that resultant, I imagined a liquid of the same shape and size. That liquid will also experience the same force from everywhere. It will also have the same resultant as this, and that resultant must be equal to the weight of the liquid, because that liquid, when it was there, it should be at rest, so they should cancel out each other. Hence, if this is equal to this and this is equal to this, this is equal to this. So the resultant of all these forces is equal to the weight of the liquid displaced. That's what it is. Now that you understand, buoyant force is not a new force. Buoyant force is not a new force. It's just the resultant of all the forces from everywhere. You should also now appreciate this fact that this solid might also have its own weight. There might be the weight of the solid. Do you think these two should be equal? Is it necessary that these two are equal? What do you guys think? The solid will have its own weight. The solid will have its own weight. Do you think the weight of the solid and the buoyant force should be equal? Is it necessary? Think again. Not necessary. It need not be equal. Yes, correcto, Dakshin. They need not be equal. In fact, think, what have you done? In that volume of that liquid which you have thrown out, which you have displaced, you have put a solid. It's quite possible. It's quite possible when you took away that liquid and in that place you have fit in a solid. It's possible in that same volume the mass of that solid is more. It's possible in that same volume the mass of the solid is more. That means the density is more. That means the solid will sink. Because in that same volume you have added more mass. So this buoyant force is not going to balance this solid's mass every time. It is just going to think, oh, there is liquid inside. Buoyant force is always a fool. Remember this statement. I'm just going to write it. Buoyant force is a fool. And what does it think? It thinks there is water, or basically that fluid in that volume. It thinks there is liquid in that volume. So it thinks, okay, there is liquid inside, so I'll just give enough force to balance the liquid. But if there is some heavy metal inside, that's it. It got deceived. The entire solid will sink. It will sink. That's how you should understand, because all these forces are still the same. It still thinks there is liquid inside. If there is a lighter solid inside, imagine if there is a lighter solid inside, what does water know? Water is always a fool. What does it think? There is liquid inside. Okay, that liquid will think there is liquid inside. So it will apply enough force to balance the weight of the liquid. But you have placed a lighter body over here, lighter solid over here. That means the buoyant force will be more than the weight, and hence the solid will come up. Is it making sense? and by chance, somehow the weight of the solid, that is the density of the solid and density of liquid, imagine both are same. So when you replace that liquid with a solid of same density, coincidentally what will happen, the weight of the solid and the weight of the liquid or buoyant force will be equal, and that's how it will stay there as it is. So that's how floating or flotation works, or that's how buoyant force works. So what is the main takeaway from this particular last 5 minutes? One is that water is a fool. What does water think? Water thinks there is always liquid inside. Buoyant force is not a new force. It is a resultant of all the hydrostatic pressure forces. Whenever you replace, the fourth thing, whenever you replace, the liquid and displace it and put a solid or something else inside, then the density of what you put inside decides whether it is going to sink, whether it's going to float, or whether it is just going to stay there. That's it. Yes, if the density is same, then it will just remain suspended in water for it. That is just like water. It's just like water. In water will always neither float nor sink. It just stays there. It just stays there suspended, correcto, completely immersed. And that's what you can find out even at home. If you have a weighing machine, just try this experiment out. Believe me, it will be so interesting to try this out at home, because you have understood Archimedes principle now. You weigh something in air. You weigh it in air. Let's say it shows 5 kg. Now you immerse it completely in water. Immerse it completely in water. Let's say now it shows 3 kg. Here the reading was 5 kg. Now the reading shown is 3 kg. You can see clearly there is a difference. What is the difference? It is 2 kg. That means on this block over here, there is a buoyant force. How much is the buoyant force? It is 2 kg. There is a 2 kg buoyant force. That's why you are seeing the weight shown is less. This weight is also called as the apparent weight. What is it called? It's called as the apparent weight. This is your true weight. This is your true weight. Okay, this is what your actual weight or true weight is. But when you are inside a liquid, you will experience a buoyant force, you will feel lighter, and this object over here has felt lighter by 2 kg. Yep. So he had weighing machines those times, just so, and there were beakers, there were containers during that time. So that's how he figured this out. Number 2, I also want you to realize the 2 kg difference will also be equal to the weight of the liquid here. Remember, there will be some liquid which will come out. Remember, there will be some liquid which will be displaced. This is your displaced fluid. This is your displaced fluid. If somebody measures that, that will be also 2 kg. Why is it 2 kg? Because think what has happened in this particular volume. You had water, but now that water has been thrown out and a solid has come. But the water around, the liquid around, what does it think? Oh, there is water inside. What does it think? It thinks there is water inside. How much kg of water does it think? It thinks there is 2 kg of water. For it, it is 2 kg of water. So it is applying a force of 2 kg upwards. That's what it is doing. So that's why the buoyant force is 2 kg. Everybody clear? Give me a thumbs up till this point. Then I will show you the formula. Everything. Perfecto. So what has happened is that when this solid was immersed, the liquid came out. The liquid around it thinks, oh, there is 2 kg liquid inside. So it will apply a 2 kg force to support it. And that's why the buoyant force is also 2 kg. Perfecto. Clear. That's what. Liquid is a fool. Fluid is a fool. Remember this statement. Liquid is a fool into thinking that there is always liquid inside. That's it. That's the key statement, a key, I would say, concept of Archimedes principle. Yes. Okay. Hemlata, no bacha, we are not going to go to problem solving without theory, because this is our nurture series, and in nurture series, it's theory and problems both. Okay. I understand some of you might have learned the theory somewhere, but there are a lot of students who are completely dependent on the theory as well as, the problem solving. So we need to do both, right from basics till high level, right from basics till advanced. So we need to do both. So does buoyant force depend on density? Let's talk about this. First of all, understand, I just told you buoyant force is the summation of all the pressure into area forces. This is one way I told you. Also remember, buoyant force is the weight of the fluid, which is displaced. The weight of the fluid which is displaced. And what is weight? Weight is mass. So mass of the fluid which is displaced into G. What is mass? Mass is density into volume. So density of that fluid which is displaced into volume which has been displaced into G. So this is your formula. So this is the formula which you are going to use again and again. What is the buoyant force? Buoyant force is the density of the liquid into volume which is displaced. You can see this is the volume which is displaced. So I can just put it over here. This is the volume which has been displaced, okay, into G. That's it. That's what the formula is. This is something which you should keep in mind. Remember, it's always density of fluid, volume which is submerged or volume which is displaced. By the way, both are same thing. If you understand, this is also equal to volume which is submerged. But this is the volume submerged for the solid. I just told that to you in the first part. Alright, yep. Hemalata, we are going to have sprint series which will just have problems. So that option is also there. Like I mentioned before, that there is going to be a sprint series which we are going to start for 11th and 12th standard students. So that will have only problems, but those of you who want theory plus the basic problems, Pathfinder series for 12th will continue. Fair enough. Shall we go ahead with problems now? Shall we go ahead with problems? Khushi, if you have joined in a little bit late, just go back a little bit behind, because I have explained in detail right from the beginning how buoyant force is equal to the weight of the liquid. So please rewind back and start watching it from beginning. Oh my God, Saja, that is too good. Proud of you, bacha. Keep it up, Saja. Keep it up. Keep it up. All right. Chalo, shall we do some questions? Okay. Now, those of you joining in late, I would request you to please go back behind and catch up at 2x speed. Going to the first question. I don't want to take an easy question first, because this question will make you understand what buoyant force is. See, even if you had partially understood it, now you will understand what buoyant force is through this question. There is a hemisphere, solid, which is hanging via a string. The flat base is facing up and it is at a depth r below the liquid. Ignore atmospheric pressure. Find the tension in the string. Find the force on the curved surface. There are some options given. Let's try to figure this out. Don't worry about these options. Let's just focus on solving the question, and then let's see whether our calculations are correct or wrong. First of all, if I ask you what are the forces acting on this particular, solid hemisphere, the first answer will be obviously there is tension. Okay, let me just put it in black. Okay, so obviously there is tension out here like this. Then obviously you have the weight of the hemisphere. So weight of that particular solid. Last thing, obviously you should also have buoyant force upwards. Buoyant force always is against the gravity. Perfect. These are the three forces. This is at rest. Use Newton's laws. So according to Newton's laws, tension, because it is at rest, so net force should be 0. Upward force, which is tension plus buoyant, should be equal to the force down, which is weight of the solid. Therefore, tension will be equal to weight of solid minus the buoyant force. Everybody agrees? Fair enough. Now, what is the weight of the solid? Think about it. Weight is mass into G, but mass is not given, density is given. So, can you not think this way? Mass is density into volume, because density is mass by volume. So, mass is density into volume. So, it is nothing but density of solid into volume of solid into G. Fair enough. That's the weight of the solid. This is mass into G. Fair enough. Minus buoyant force. What was buoyant force? I told you it is always density of fluid into volume which is submerged or displaced into G. That's all I have done. I have just used the formula, nothing great about it. Now just start substituting and see what you get. What is the density of the solid? The density of the solid is given to be 2 rho. Density of fluid is rho. So density of solid, that is 2 rho, into volume of the solid. Solid is nothing but a hemisphere. Sphere's volume is 4 by 3 pi r cube. Hemispheres is half of that. So it will be 2 by 3 pi r cube into G minus density of fluid. It is mentioned as rho. So just put rho over here. Submerged volume. Everything is submerged. So whatever is the volume of the hemisphere, that is the volume submerged. So it will be nothing but 2 by 3 pi r cube into G. Now observe, 2 by 3 pi r cube, 2 by 3 pi r cube is same, Gg is same, rho is same. So 2 minus 1 is 1. So it will be just rho into 2 by 3 pi r cube into G. So that is basically your tension. So I think we have figured this out. So the value of tension is 2 by 3 pi r cube G. 2 by 3 pi r cube G. Perfect reduction. Got it till this point? So I think tension is done. Tension is done. So I'll just put the value of tension over here. So the value of tension that we got was 2 by 3 pi r cube rho G. I don't think I need this anymore, because for the second part something else only is asked. Force on the curved part of the hemisphere. Now for that I want you to think, why will there be a force on the curved part? The force on the curved part will be there because of the pressure forces. Think, this point will have some pressure here, this point will have some more pressure, so more force, some more force over here, some more force over here. Again the force will keep on decreasing and so on and so forth. So the pressure of the liquid will create a force on all the parts of the curved surface. This is how the forces will look like. Can you imagine by symmetry? These forces are similar, these forces are similar, these forces are similar, these forces are similar. And as you come down, the forces keep increasing. So by symmetry, can you visualize where would the net of all these forces be? The forces on the curved surface. So these are the forces on the curved surface. Where do you think the resultant should be? Just by logic, think about it and let me know. Come on, my warriors, figure this out. Where do you think the resultant of all these forces must be? And no, I'm not asking where it will be, I'm asking what will be the direction of it will be. These forces will have x and y. All the x components will cancel everywhere. No, you don't have to do integration. Each force has x component, y component. Each force has x component, y component. Can you see the x components will get cancelled? And this will add. So every force will have y components which will get added throughout the curved surface. So the resultant must be upwards. So hence I am going to show a resultant force like this. So this is the net force on the curved surface. Okay, so this is basically your net force. This is what we want to find. Now I'll be like, sir, how do we do this integration? Nah, not needed. I'll tell you why. See, I'll give you a simple logic. Guys, there is also a force on the flat surface acting down. There is also a force on the flat surface acting down, correct? So there are these forces acting on the flat surface as well, and there will be a resultant of all of them. Now, if I ask you, what is the resultant of this flat force and the curved force? This is the net force due to the pressure acting on the solid. Think, if I ask you, what is the force on the curved surface that is acting up, and this is basically acting down, flat surface. If I add them up totally, because curved is up, flat surface force is down. If I add all these forces, what is the resultant going to be? The resultant, no, it's not going to be the tension. Forget the tension. Just forget the tension for now. Just imagine any solid which is immersed in a liquid, the net force of all the resultant, all the forces due to the pressure, what is it called? The net force due to all the pressure forces acting on all the surfaces of the fluid. What is it called? That is called as the buoyant force. Exactly, NV18. This is nothing but the buoyant force. This is just the buoyant force. So there is no need of tension. There is no need of mg over here. That's what I want you to understand. Everybody fine? Give me a thumbs up or give me a yo till this point if you have understood this equation. This equation has just come because the net force due to hydrostatic pressure is nothing but is called buoyant force. It's called buoyant force. That's the reason for that. That's it. Welcome Nitya. I'm guessing you were attending it before as recorded, but even if you are attending for the first time, welcome aboard. Perfecto, my warriors. Very good. Now, what is the force on the curved surface? I don't know. What is the force on the flat surface? Force on the flat surface is pressure at that flat surface into the area of that circle. Remember, it's a circular base, so area of that circle. Buoyant force is density of the fluid into volume which is submerged into G, standard formula. So what do we get? So the force on the curved surface will be E minus this pressure. What is pressure? Pressure is rho GH. Remember, we have to ignore the atmospheric pressure. So ignore the atmospheric pressure. So it will be rho GH. Rho is rho, G is G. H, what's the height? What's the height of this circular base? It's at a distance of r. Can you see that? It's at a distance of r. So into r. Area of the circle is pi r square. This is equal to density of fluid, which is rho. Volume submerged, which is half the hemisphere. So 2 by 3 pi r cube into G. So this becomes the complete equation. You can see rho is there. R square and r will become r cube. Pi is also there. And G is also there. So the force on the curved surface will become rho is common, pi r cube is also common, G is also common, and when this goes on that side it will become 1 and plus you will have 2 by 3. 2/3 plus 1 is 5 by 3. So this will become 5 by 3 rho pi r cube and G. Is that understood though? Is that understood though? Mangalam, remember my classes have now shifted to 7 o'clock instead of 7:30. So all those of you are joining in right now, remember classes start at 7 o'clock for Cap to Shreyas. Yep. So pi r square is also common and r is also there. You can see r and r square will become r cube. Here also it will become r cube. G is also there. G is also there over here. Okay. And rho is also there. So that will also come outside. So 1 plus 2 by 3 is 5 by 3. Perfecto. So that's how we have done this question as well. So 5 by 3 and 2 by 3. So let's see whether that option was there somewhere. Yep, it is there. 2 by 3 was the first answer. 5 by 3 was the second answer. Done, done. After solving this question, I doubt you should have any confusion about how buoyant force acts and what exactly is buoyant force. Now, remember the entire PDF will be uploaded on the Telegram channel. The link is there in the description box. And yes, if you need any further assistance, you want to solve more problems and you want to cover up your entire syllabus and also want to continue with the revision of 11th and then move on to 12th standard, remember our pro subscription courses are still open and you can join the batch which has just started last week for 11th standard. And that batch will continue as 12th standard batch till 2023 JEE. So do not forget to check out the link which is there in the description box because the course prices are as low as 1,300-400 rupees per month. Okay, so let's talk about flotation now. When you take some boat or wood or some plastic or even a human, you have seen that they float. Now let's write the equation for floating and let's figure out what exactly is happening out there. Just imagine there is some object which is floating out here. What are the forces acting on it? One is its own weight. Second is the buoyant force from below. If it floats by chance, if it floats, then what can you see? you can say that the weight of that particular solid which is acting down should be balanced by the buoyant force which is acting up. Correct? Now, what is the weight of the solid? Weight of the solid is mass of the solid into G. What is the buoyant force? Buoyant force will be volume which is submerged into density of the fluid into G. You can see GG anyways cancels out. Okay, GG anyways cancels out. So this is the condition for that. Now, if you want, you can simplify this and you can write mass. You can write mass as density of solid into volume of solid. Now please remember one thing. This term and this term won't cancel. Do you think is the volume of solid and volume which is submerged, is it equal or not equal? Put it up in the chat box. Think. Is the volume of solid, which is there over here because mass is density into volume, is this volume of the solid equal to volume submerged? Definitely not equal. Okay, it might be equal, it might not be equal. If it is equal, then think that it means only one thing. If these two are equal, then these two should be equal. And if these two are equal, that means the entire solid will be just under water and it will be suspended like this. This will only happen when density of fluid and density of solid both are equal. Got it, my warriors? So when both are equal, then it will just stay underwater. It's like, have you ever played Holi and have you ever played with water balloons? You would have seen that the water balloons just stay in the water wherever you leave it. It just keeps on floating. So that's basically this example. But wood will come out of water, that will be called as partially submerged. What is this situation called? This is called as partially submerged. This is partially submerged. This is completely submerged. This case is also called as completely submerged or completely immersed. And if by chance the density of the solid is more than the density of fluid, the solid's density is more than the density of fluid, then yes, it's going to sink below. So keep this in mind. So the net force acting on any object immersed in water will be the weight of that solid minus the buoyant force. Weight will act down, buoyant force will act up. So mg minus rho vg, this is solid's mass, this is the buoyant force. If F net is positive, that means the body will sink. That means the net force is downwards. If F net is negative, then the body will rise up. If F net is 0, then the body just stays as it is wherever it is. And I have put this up for all of you in this beautiful image out here. Yep. Look at this beautiful image. This will float when the solid's density is less than the fluids or the medium's density. It remains suspended when the density is same, and it sinks to the bottom of that river when its density is more. I have a brilliant question now for all of you, and here it comes. Okay, so get ready, warriors, because we have an amazing question for all of you. Okay, but before that, I have one small doubt. Probably you can answer this. What is ship made of? Is it made of wood? Big ships. Is it made of wood or is it made of metal? What do you guys say? What is ship made of? What is the ship made of? Is it made of wood? Is it made of plastic? Is it made of metal? What do you guys say? Obviously, the smaller boats are made of wood, but the big ships, the big ones, if you have seen, they are made of steel. They are not made of wood. No, Ramya, that's wrong. They are not made of wood. They are made of steel. They are made of metals, alloys. Correcto. Why is it made of metal? Why not wood? There are multiple reasons for that. Okay. One is, wood is not as strong as metals. If ships collide and if there is a very rough weather, then the wood can break. Also, the wood can decompose. So many things are there. It's made of, very strong alloys. Now, the question is, metals sink. We know that metal's density is more. So it will sink. So the object will behave just like this yellow one over here. But how is it possible that the ships stay afloat? What is the reason behind that? What is the reason behind that? The reason behind that is, what is the reason behind that? Think about it. Okay? Chalo. You think carefully and probably you can leave the answers in the comment section below. Okay, here we have the question. And like I was telling you, beautiful question. There is a body of density 3 rho. It is completely submerged in a liquid of density rho and then it is released. What is its acceleration? Let's think. So the density of the body is more than the density of the liquid. That's why it is accelerating. That's the first thing that you should understand. You should think, why is it accelerating? The reason why it is accelerating is because the density of the solid is more than the density of the liquid. Now, what are the forces acting on this? One is the buoyant force. Second one, obviously, will be the weight, and the weight will be more, and there will be some acceleration downwards. So, by using Newton's laws of motion, one can say weight minus the buoyant force is equal to mass into acceleration. F is ma. What is the weight? Weight is mass of that solid into density of that solid. Mass of the solid. Mass of the solid is density of the solid into volume of that solid into G. Buoyant force is density of the fluid into volume which is submerged into G is equal to mass. This is mass of the solid again. So which is again density of the solid into volume of that solid into A. Now one very interesting thing is going to happen, and that is the volume of the solid, volume which is submerged, and volume of the solid will get cancelled everywhere. You might be wondering, sir, volume of the solid and volume submerged is not equal. Think carefully. This is completely submerged. This is completely immersed. So whatever is the volume of this solid is equal to the volume which is displaced or volume which is submerged. So hence they will all cancel out. Now it's just a matter of substituting the values. The density of the solid is 3 rho into G comes as it is. Density of fluid is rho into G, and this is density of solid again, which is 3 rho into acceleration. Rho also will get cancelled, like you can see from everywhere. So 3G minus G is nothing but 2G. So 2G is equal to 3A. So therefore A is equal to 2G by 3. So that's the acceleration of that body downwards, which is option A. Done, done, done. Perfecto. Excelente. IT aspirant will discuss about viscosity in one of the next class. Yep, we're going to come to that as well. So we're going to complete dynamics. After dynamics, a separate lecture just for viscosity. Okay, very good, my warriors. Welcome aboard. So it's not about, I'm not sure what you are referring to, Vivek. You can be more elaborate and you can tell me which question you are referring to. Or are you referring to the question which I asked about the ships? Well, that's not the scenario. If you are answering to the ships question, that's not the correct answer. Okay, think about it again. Well, the actual reason why the ships end up floating in spite of being made of heavy metal is that it's not completely solid. See, if this is the boat, this is not solid. There is air inside. There is air inside. It's hollow. Most of the ship is hollow, right? So because of which, even though if it is made of metal, effective density comes out to be less than the density of water because of the hollowness. That's what you do. So you make the ship so large, or basically you make sure that the volume enclosed inside the ship is so large that the effective density comes out to be much lesser than that of water. That's why it behaves like a solid which is less dense than water, and it effectively floats or partially submerges in the liquid. Is that making sense? Sharan, I gave the schedule yesterday in my strategy session. Just watch the strategy session which I conducted yesterday. I've given the entire schedule. Perfecto. Now here we have the next question coming up on your screen. A block of wood floats with 3/3 of its volume inside water, but when it is put in oil, then it just floats. The meaning of just floats is that, it is completely submerged. It is barely managing to float. It is suspended. The question is, what is the density of the oil? The question is, what is the density of the oil? Let's see how many of you can do this question coming up on your screen. Come on, my warriors, figure this out. How will you do this? Let's take both the scenarios. A wood floats with 3/5 of its volume inside water. Okay, so this is your water and this is your wood, and it floats with 3/5 of its volume. So this is 3/5 of volume, and this entire thing had a total volume of V. This is your wood. Okay, so this is basically your wood. Now think that this is water. This is the first situation. This is water. Now in the first situation, what is happening is that the weight of the wood, the weight of that particular wood is being balanced by the buoyant force of essentially water. This is balanced by buoyant force of water in the first scenario. In the second scenario, what has happened? Think, this is oil. The solid, that wood, barely floats, just floats. That means it is completely immersed. This is how the wood looks like in the second scenario. And if it is floating, obviously, still the new buoyant force because of that oil should be balanced by the weight of the wood. Make sense? It is at rest. Now, just use Newton's laws. That's the most important chapter. It comes again and again. So think, in the first scenario, the buoyant force is balanced by the weight of the wood. Second scenario, the buoyant force is balanced by again the weight of the wood. The weight of the wood, did it change? It's the same wood, it's just that the liquid changed. The liquid changed, but the solid did not change. That means, if in the first scenario, the weight of the wood was equal to the buoyant force by water, correct? And in the second case, the weight of the wood was equal to the buoyant force by the oil. Hence, these two must be equal. So the buoyant force by water must be equal to the buoyant force because of oil. Now, what is the buoyant force because of water? Think, it is density of water. Then what is the density of water? Density of water is 1000. So I'm just going to put 10 to the power 3 into volume which is submerged, which is 3/5 times of V into G. So that's buoyant force of water, straight formula, V rho G, rho Vg, whatever you want to call it. Hi Sidhu. And here we have, what is the buoyant force because of the oil? Buoyant force because of oil is density of oil, which I do not know, into volume submerged. In this case, it is complete V. The total volume V just got submerged into G. Can you see what and all got cancelled? So we can see V, V, G, G got cancelled. So I'm just left with density of oil. So what is the density of oil finally? 10 to the power 3 into 3 divided by 5. This is 1000 divided by 5. What is 1000? What is 1000 divided by 5? So that is going to be nothing but 200. So 200 into 3 is 600. So hence the answer is 600 kg per meter cube. Correct. It is option C. This is the density of water will not be given. You should know that. Density of water is always 1000 kg per meter cube. Something which you should always know. Perfecto Sidhu, perfecto IT aspirant. So that's how you start solving problems. Now that you are slowly understanding how things are to be solved and what is buoyant force, let's scale it up and let's solve some more problems. Okay, perfecto, we got the answer as C. Moving on to the next one. Thank you, Samyukta. Now this diagram is so beautiful that I want you to really appreciate and also learn a trick from this diagram. They always use a phrase saying this is just the tip of the iceberg. Especially when you're discussing something and you just get to know something is fishy between these people or something fishy is going on somewhere. And then you might have heard about this phrase. This is just the tip of the iceberg. Meaning there is so much more that you still don't know and you've just started to understand what the thing is. That means there are a lot of things you do not know. So whenever you see an iceberg, just imagine you don't see all of this. It looks so massive and so nice, but there is so much more even beneath it. Now, why I want you to remember this diagram is because it will help you for solving some nice questions like this. Imagine if I ask you what is the density of ice. The density of ice is actually 900 kg per meter cube. The density of water, okay, is 1000 kg per meter cube. If you apply Newton's laws and you solve the question like this, okay, the weight of the iceberg is equal to the buoyant force because of the water. When you solve this, what you're going to get is a very interesting term. You're going to get the density of ice upon density of water. Guess what this is? Density of ice upon density of water will be volume of ice submerged. Volume of ice submerged upon the total volume. That means if you observe here, density of ice is 900. This is 900. Density of water is 1000. This ratio will come out to be, for this particular scenario, 900 by 1000, which is 9 by 10. That means 90% is inside and hardly 10% is outside. That's how you should remember this. And why is it important? Because whenever water is given or some other object is given which is immersed in it, then if you know what is the density of that object, immediately you know in percentages how much percent is immersed. For example, if somebody tells you, it's wood whose density is 600, you should immediately think 600 is 60% of 1000. 600 is 60% of 1000. That means 60% wood will be inside, 40% wood will be outside. Isn't it making things very simple? Got it? No problem, Mohan Raj. Just rewind back and catch up at 2x speed at least to the current place. Yep, Dakshin, that's a real pick. Perfecto, right? So this is what you should understand, that whenever you know the density of solid relative to the density of liquid, you express in terms of percentage, that will be also the percentage of the volume which is inside. That's what you have understood right over here. Here is the question coming up on your screen. We have a brass cylinder. It weighs 60 grams in air. If the density of the brass is 5 grams per cc, what do you think should be the weight of the cylinder in water? Perfecto. No, the density of oil can be anything. It depends on which oil you are using, castor oil, coconut oil, so it depends. So according to the problem, things will change and you don't have to remember the density of oil. But density of water, yes. Now, what you should do is draw the free body diagram. This is your brass cylinder. Okay, this is your brass cylinder, and the brass cylinder will have its own weight. What is the own weight of the brass cylinder? It is 60 grams. So 60 into G. Let's keep everything in CGS unit because everything is in cc, grams and all of that. Okay. There will be also a buoyant force upwards. So there will be a buoyant force upwards, and because of this, the brass will weigh less. So if somebody uses a pan over here, a weighing machine over here, then that weighing machine is going to show lesser weight, correct? The weighing machine is going to show lesser weight because that 60 grams is down, but you are supporting it with the buoyant force. So I can say the apparent weight, not the real weight, the apparent weight. Remember I told you it is the real weight minus the buoyant force. I gave it to you just some time back. The weight minus the buoyant force, whatever is remaining is the perceived weight inside the liquid. Now think about this. what is the real weight? Okay, so the question is, what is the weight of the cylinder in water? That's what they have asked. What is the apparent weight? What is the weight of the cylinder in water? Apparent weight. Real weight is known. It is 60 into G. Buoyant force is density of liquid, which is basically in this case water, into volume of brass. So volume of brass, which is completely submerged, into G. Fair enough. This will now become 60 minus, because G is common. Okay, density of water, volume of brass, it's not given, but density is given. I can do something over here. And what is that something? Think. Density of brass is mass of the brass upon volume of the brass. So density of brass is known. Mass of the brass is also known, 60 grams. So can't I find the volume? Correct? So just put the volume of the brass as mass divided by density of brass. That's it. This entire thing, because G was taken out common, it goes over here. Now the next step is just substitution, and let's see what do we get. So 60 bracket is also put. Density of water, it's 1 gram per cc. Everybody knows this. Mass of the brass, it's 60 grams. Density of brass, it is 5. This entire thing into G. 60 comes outside. So 60 and 1 minus 1 by 5 is 4 by 5 into G, which is, this 5 goes with 60 12 times. 12 fours are 48 G. So 48 G is the force or the weight. So in grams, it will be 48 grams. That's the answer. Perfecto. Hello Kalyani, my timing has shifted to 7 o'clock. So all my lovely warriors, do not forget to join in at 7 o'clock every day. Got it. Perfecto, ID aspirant. Very good Dakshin. Very good Manvi. Excellent, my warriors. Good evening, Kiran. Welcome aboard. Welcome aboard. So this is how the question is. Perfecto. This is very, very interesting. And let me tell you, why is it interesting? Because this is how, this was the basis of figuring out, whether some impurity is there in that solid or not. If you know the density of solids, imagine if you know the density of solid, if you know density of fluid, if you know the volume, etc., then inside water it should weigh something, inside air it should weigh something. But if it does not weigh that much, then you know for sure that there is some impurity. So when Archimedes basically ran out of water naked around the town, actually what happened before that is that the king had given him a task of figuring out whether this crown is made of pure gold or not. So that's when he thought about it for days and days, and then when finally it clicked that there must be a buoyant force upwards, he used that buoyancy principle, he used his own principle, and then he figured out, oh, this is the way I can actually figure out whether there is some impurity or not. Because the moment there is some impurity, the apparent weight will not come out to be as expected. It will differ from it because there is some added copper or brass inside it. So because of which you will get a different reading, and that's how you can figure out whether that solid is made of pure gold or not. That's how it is. I'm very good. Thank you, bacha log. Okay. No problem. So I did not understand something in wave chapter. So Dinesh, there is a separate lecture for waves, bacha. You can definitely watch my wave optics. And in fact, I'm going to continue wave optics this week. Okay, so don't worry about it. Sundar, I'm doing very good. I'm seeing you guys after a long time, by the way. Sundar, Manvi and Kalyani and so many others. Welcome aboard. Yep. Now, let's talk about Dead Sea. Have you heard about Dead Sea? What's the speciality about Dead Sea? The speciality of Dead Sea is that the water has so many minerals, so many salts that are dissolved in that water that, the density becomes very high. And because the density is very high, you end up floating in that liquid. Yeah. Look at this guy. This is how you can float. You can read a newspaper. Even if you do not know swimming, you can still float without any worries. It's almost impossible to sink or drown yourself in Dead Sea. That's the most fascinating thing about Dead Sea. So maybe you should add it to your bucket list for traveling. Now imagine a Pandu who goes on a vacation. He goes on a vacation. He once goes to maybe Goa, and then he goes to Dead Sea, and maybe then back at his home he has a nice swimming pool out in his house. So 3 places: Dead Sea, Arabian Sea, and freshwater pool. This is your Pandu. The question is, if Pandu can float in all the 3 things, he's just lying down there, where do you think will the buoyant force be highest? Where do you think the buoyant force will be the least? Arrange it in ascending order. Arrange it in ascending order. So basically wherever the buoyant force is least, put it first, and then you can slowly increase it. The gamers, you can find it on Google Maps. You'll get the proper location. You can zoom out of the map and you'll get a better purview. Yes, our Pandu has come. Come on, my warriors, what do you guys think should be the correct order of the buoyant force acting on Pandu? All right. Come on. Think. NV18 saying 1 more than 2 more than 3. Interesting. Dead Sea has more buoyant force than Arabian Sea, than freshwater. That's what he says. What about others? Dakshin also saying 1, 2, 3. Is it? Let's figure this out. Come on, my warriors. Think about it carefully. Are you sure about this? What is buoyant force? The buoyant force is the density of liquid into volume which is submerged into G. So this Pandu, wow, what a snap. I caught Pandu at the right moment when he was just about to throw out that liquid. So this is our Pandu. Okay, this is his half pant or swimming wear. This is how it is. Pandu had asked me not to disclose the color of the swimming costume that he was wearing, so I'm going to draw it in black and white. Okay, I hope you make peace with that. Fair enough. So this is basically the volume which is submerged. That's what it is. This is the volume which is submerged. Now, where is the density highest? Obviously, the density of Dead Sea is very high. I just told you. Then comes Arabian Sea, which has lesser salts in it, but it is more than water pool, because water pool will be fresh water. So density of pure water is least. Then comes Arabian Sea, and then comes the Dead Sea. So whichever has more density must have more buoyant force is what many people think. But you guys forget that it also depends on the volume submerged. So think about it. Think about it. In Dead Sea, actually speaking, even though the density is high, the volume submerged will be less because he will float more. In fresh water, the density is less, so volume submerged will be more. Think about it. Correct? Now you will be like, sir, now how do you figure out? One is increasing, one is decreasing. I do not know whether they compensate. I will tell you a very simple tactic. What are the only 2 forces acting on Pandu? One is the weight of Pandu. One is the weight of Pandu, which is acting down. And what is it balanced by? It is balanced by the buoyant force which is acting upwards. Is the weight of Pandu going to differ? Is the weight of Pandu different in pool, different in Arabian Sea, different in, this is a true weight by the way, different in Dead Sea? No, right? It's the same. So if the weight of Pandu did not change, the net buoyant force must be same. So hence the answer is, it is same. It is basically same everywhere. So density into volume the product will be constant. That's what it is. It is equal. Perfecto. Yep. So lovely Kiran, I have just follow the order of my Pathfinder series. There is a playlist of Pathfinder. Just follow the same order, and that's how you should complete your 12th standard syllabus. Okay. Yes, Manvi, I give homework problems towards the end of the class. And yes, if you want more problems, then you know what you should do. Check out all the pro subscription assignments and also the Tattva module. So if you are already a pro user, you will be getting a soft copy of this entire book for each subject and for each chapter. This has thousands of problems, crazy problems, so you should solve this book for more assignments. This has easy to medium to advanced problems along with P1Qs. Okay, here is the next question. Comment on the water level if the ice melts because of heating. So let's say the ice melts, it's earlier floating. So what do you think will happen to the level of water? Okay, it's in a beaker. Just think about this like a beaker, and you can measure any small changes that happen. Will it go up, will it go down, or will it stay there? So if this iceberg melts, okay, just imagine this ice or iceberg is kept in a beaker or a container, and I'm asking you to figure out whether the level of liquid increases or decreases, or it remains same, or it cannot be said by the given piece of information. Gokulnath, that is amazing, bacha. I see you being really fond and doing really well with maths, and I'm pretty sure that math subject is going to help you with physics as well as chemistry at such an young age. Very good. Okay, if the part is included, everything I'm talking about initial level. Right now the level is somewhere here. Now it melts. After some time you come back and see at the liquid level. Now what is it? Is it going to be more or is it going to be less? Hello Rihan. So guys, let's have a look at the answer. First of all, okay, there is some liquid which is displaced. Okay, just think of it this way. Imagine that container. Okay, just imagine this container out here. This is our container. And let's say there was no liquid. There was no iceberg in it. So the level of liquid was like this. So the level of the liquid without the iceberg is only this much. The moment you add the iceberg, you can see some amount of water is displaced. So basically you can quickly see over here, this is the amount of liquid which is basically displaced. Okay, this is the amount of liquid which is displaced. Now if I write the equation for buoyant force on that iceberg, that will be nothing but equal to the weight of the iceberg. The weight of the ice which is acting down should be balanced by the buoyant force. This is because it is at rest. Okay, this is the first scenario. Now when the ice melts, it becomes liquid. Just assume that liquid to be like a solid, just for now. Even that liquid will float. So when it melts, the melted ice will also float. That means it is still going to be at rest because it is floating. Makes sense? Because it is floating. That means that melted ice is still at rest. So that weight must be balanced by the new buoyant force. That weight of the melted ice must be balanced by the new buoyant force. Everybody agrees with this? But when ice melts into water, obviously the mass remains the same. Mass is nothing but the same. If mass is same, weight is same. If weight is same, RHS is same. If RHS are equal, then what is equal? This is equal. Do you agree with this? This is also going to be equal. And if these two are equal, what does it mean? It just means the displaced liquid is also the same. If the displaced liquid, whether the ice melts or whether the iceberg stays, if it is the same, the level of water will remain the same. So basically the answer is it remains the same. Correcto. I'll just repeat again. The first scenario was when the iceberg was just put in that water. Just imagine first the iceberg was not there, you just put it in the water, the liquid gets displaced. So the buoyant force will be equal to the weight of the ice. Second scenario, again you take out that iceberg, melt it, and that melted iceberg again you put it back, or let that iceberg melt wherever it is. Again that melted ice will float in it. So the new buoyant force will be equal to the weight of the new ice which has just melted. That's it. The mass won't change because it's the same ice which melts. Volume might change but the mass won't change. Weight won't change. So LHS is same. And what is buoyant force going to depend on? It is V rho G, volume submerged. So displaced fluid is the same. So the level won't change. Is that understood? So a lot of people make a silly mistake out here. They think it is going to increase. Now if you do not believe me, just do one thing. Just leave ice in a jar of water and mark it. And then come back after 1 hour and see the level of the water inside that beaker or that container. Once that ice melts, you will see it will not change. Yes, believe it, it won't change. Okay, and the reason I've just explained it to you over here. So it remains the same, perfecto. Let's go to the next question. And this is slightly more advanced than the previous one. A wooden block, this one, is floating and there is a coin on top of it. As shown, the amount of wood which is submerged in water is L. The coin is over there. After some time, somebody just drops that coin. So the coin falls over here. So what do you think will happen to this L? What do you think will happen to this H? Will it increase or will it decrease? Yep, girl, we'll have classes every day, bacha log. Come on, think about it now. What do you think is going to happen? One of them is very obvious. Guys, think this way. If this coin falls down, this length, what will happen to this length? Come on, at least this you should be able to answer. If this coin falls down, the weight which is down will decrease. So what will happen to that wooden block? What will happen to that wooden block? It will come up, right? So if the coin falls, once the coin falls, we all know that the wooden block will definitely, it will come up. It will come up, and the moment it comes up, the length will, this length will decrease for sure. So L will decrease. Fair enough. Now you'll be like, sir, if length decreases, then I know, sir, what will happen, because now lesser volume is submerged. Lesser volume is submerged. So what will happen? The level of liquid will come down. So a lot of people think as soon as the coin falls, this box goes up, the wood goes up, so the level of water comes down. But you guys forgot one thing. The coin will also fall in the water. Because the coin falls in the water, again it can come up. Now whether it compensates or doesn't compensate is another theory. Let's figure that out. Lovely Kiran, like I mentioned, follow the order of my Pathfinder playlist. There is a playlist, just go to playlist tab. Just click on Pathfinder series, the same order, right from electrostatics to electromagnetic waves, follow exactly the same order. Now, here is the thing. What will happen to the height? I have a logic for it. Okay, so before, this is before, think the weight of the wood plus the weight of the coin. The weight of the wood and the weight of the coin was exactly balanced by the buoyant force in the first scenario. Correct? The buoyant force by the liquid was balancing the weight of the wood and the coin together. Now, afterwards, once the coin falls, what happens? Do you think the weight of the wood plus the weight of the coin, is it more than, equal to, less than the net buoyant force on both of them? Once the coin falls down, do you think the buoyant force, the total buoyant force, is equal to or less than or more than the total weight? What do you think I should put over here? Think carefully. What do you think I should put over here? Symbol. Is it equal or is it not equal? I'll give you a hint. The coin is sinking. Remember, it's a coin, it's a metal coin. It is sinking. If the coin sinks, that means the weight of the coin cannot be balanced by the buoyant force. The buoyant force is not sufficient to balance the weight of the coin. If it is not sufficient, that means the weight of the coin and the wood together is more than the net buoyant force. Think about it this way. See if you guys got it. Earlier, the wood and the coin were floating. The wood pushed the water down, more fluid displaced, because of which buoyant force was able to balance it. The moment coin falls down, the net buoyant force has reduced. Why? Because the coin is sinking. If it is sinking, it's not able to displace enough water. So the new displaced water, into you can clearly see is less than the displaced water in 1. So basically, once the coin falls, the level of liquid, the level basically goes down. That means H also goes down. See if this makes sense. Got it? Because this is equal to this is equal to this. So FB1 is more than FB2. FB1, if it is more than FB2, so displaced fluid is more than displaced fluid the second time. That's it. As simple as that. Clearo? Done. So hence H will also decrease, L will also decrease. Perfecto. Let's get moving to the next one. Okay, beautiful question. So the idea was when the coin falls down, the buoyant force is not sufficient because the displaced fluid is not sufficient. So you are not displaced enough fluid. So the level has gone down. Got it. Perfecto. Moving ahead to the next one. Now, let's talk about a concept called as center of buoyancy, and I have two amazing questions. Are you guys now ready to do two amazing questions? Very good level questions. Here it is. That is center of buoyancy. You might have seen if you drop a pen or some floating object in liquid, you will see that it somehow aligns or orients itself in a peculiar direction. It's in a very peculiar direction. Even if you try to rotate it, it will again come back. You might have seen some videos on YouTube where, the ship is passing in a storm or a boat is going in a rough water. In spite of that, in spite of the boat twisting left and right, it again comes back to its natural state. Sometimes when something is floating and you give it a punch, it will just fall off. You might have thought, hey, why is this happening? Why do certain objects, tend to come back to their original state? Some objects do not tend to come back to their original state. Something is wrong. And what is the theory behind it? The theory behind that is center of buoyancy. Center of buoyancy. Now, what is the center of buoyancy? The center of mass of the fluid which is displaced. The center of mass of the fluid which is displaced is called center of buoyancy. You'll be like, sir, I did not get it. What do you mean by that? I'll tell you. Let's break it part by part. The fluid which is displaced. What is the fluid displaced? What is the fluid displaced? In this case, when the ball is floating, this is the fluid displaced. This is the fluid which is displaced. That much part of the fluid will have its center of mass. The fluid will have its own center of mass. So this is the center of mass of the fluid. The center of mass of the fluid. That's where the center of buoyancy is, and that's where your buoyant force will act. So the buoyant force will act from here. The buoyant force acts from here. But remember, this is not the center of mass of the solid. In fact, the solid could be anywhere and the center of mass could be also anywhere. So this is the center of mass of the solid. And from the center of mass, what do you have? From the center of mass, you have the weight of the solid. So these two things are different. Center of mass of solid and center of mass of liquid which has been thrown out. Both are different. Both are different. This one is called center of buoyancy. This is center of mass of the solid. Keep this in mind. Now, depending on where the center of buoyancy is relative to center of mass, the object may topple or may not topple. And I'll show you a simple photo. Look at this. Look at this. This is a solid which is floating in a liquid. Observe this carefully. This is the center of mass of the solid. This is center of buoyancy. That means it is the center of the displaced fluid. Observe. This one is the displaced fluid. This is the center of that. Perfect. Now imagine somebody topples it. Somebody rotates it. Now what will happen? Think this way. Somebody topples it. Now you can see more fluid is displaced on this side. The center of buoyancy will also go here. Just look at this submerged part. You can see more fluid is submerged here or more solid is submerged here. Center of buoyancy goes there. Center of mass of the entire solid is somewhere here. From center of mass of the solid, what do you get? You get the weight. From center of buoyancy, you get the buoyant force. Do you see these two forces are not in the same straight line? Do you see both these forces? Earlier they were in the same straight line, but the moment you tilt it, one of the force went there, one of the force came here. Do you see they are not along the same line? What will they create? What do you think? What can you feel? What can you gauge out of this? What is it trying to create? Is it creating something? I think it is creating something. Try to get a feel of the situation. I think there is a torque out here. So clearly there is a torque which is trying to make it come back. Do you see that? So that torque will try to pull it back to this original state. That's why it stays as it is. Correct, Mukund? So this is the idea behind center of buoyancy. So when the center of buoyancy is lower than the center of gravity, and when you tilt it, you will see that the torque produced by the buoyant and the weight force will pull it back to its original state, and it will remain stable. It will remain stable. So keep this in mind. Okay, so that's what buoyant force is all about. Perfecto. So buoyant force always acts from the center of buoyancy. Keep this in mind. Charu, you are going to get the previous session PDF. Don't worry, you will get it. Here's the question coming up on your screen. Yep, it will be up by tonight, Charu. Don't worry. This is a rod which is hinged here and it is floating. Why is it floating? Because density is less than the density of the liquid. It makes some angle theta and the length of the rod is L. This height is L by 2. Question is, find the angle which it makes, 90, 45, 60, 72. Let's try to figure this out. Now I don't need those options, so I'm just getting rid of it because I'm going to need some space. Let's try to draw the free body diagram first. Without that, we cannot do anything. Now, there are two things to remember. This rod is not basically sinking, it's at equilibrium. So the net force is 0 and net torque is 0. But the problem is I do not know the force acting on the hinge. So I don't think I can go with forces, because if I balance all the forces, buoyant, weight, etc., there is this reaction force which I am unaware of. So the best thing to do is to go via torque, and I know that the net torque is 0 because it is not going this way nor going that way. Fair enough. So whose torques will be considered? If you measure the torque about this point, even if there is a reaction force, do you think the torque will be taken into account? Do you think the torque of the reaction force will come? No, right? Because it is passing through the hinge. So this torque will not matter. One torque is the weight of the rod itself, clockwise. The other torque is the buoyant force, which is anti-clockwise. So one thing is very obvious. The torque of mg, which is clockwise, is being balanced by the torque of the buoyant force, which is anti-clockwise, because it is in equilibrium. Everybody agrees with this. Everybody agrees with this. So we need to figure out what these torques are, and probably when we write these equations, we are going to get the value of theta in terms of sine, cos or tan. Now, where is the gravitational force going to act from? It will act from the center of mass of the entire solid. Now think carefully. This is the length. Half the length might be somewhere over here, or I don't know, maybe it could be here also. Okay, this is where the center of mass of basically the rod is. This is where the center of mass of the rod is. Let's say I'll put it over here. Okay, maybe somewhere over here, because this is L by 2. So L by 2 might be somewhere over here. So I'll just put it like this. This is weight of the rod. Fair enough? Perfect. Now when we write the torque due to the weight of the rod, I would need the perpendicular distance. Think about it. I will need the perpendicular distance right over here. Now how much is this perpendicular distance? Think this way. Guys, from here to here was L. This is center of mass. So from here to here, will it not be L by 2? Think about it. This much part will be L by 2, right? From here to here. So if that's the scenario, think, if this much is L by 2, this part will be L by 2 cos theta. Won't it be L by 2 cos theta? Everybody agrees with this. So can I say the torque because of the rod's weight, about this point will be this perpendicular, R perpendicular. If there is R and F, you always draw perpendicular. R perpendicular into force is the torque. Remember this. So that perpendicular distance is L by 2 and the force is the weight of that rod. Perfecto. I will write the RHS later on. Let's think about LHS first. What do you think is the weight of the rod? What do you think is the weight of the rod? The weight of the rod is the mass of the rod into G. But what is the mass of the rod? The mass of the rod is the volume of the rod into density. So the weight of the rod is density of the rod into volume of the rod into G. Fair enough. Therefore, L by 2 into density of rod is rho. Volume of rod, I do not know, but imagine if somebody tells you, just assume that the area of cross section is small a. Area of cross section, this is the area of cross section of the rod, is small a, the length is L. So what will be the volume? Area into length, right? So area of cross section into length. So can I say this volume of the rod is area of cross section into the length, and this is G as it is? Fair enough, everybody, till this point? Okay, but I think I had to put L by 2 cos theta out here. So let me just start from the beginning. I'm so sorry guys, I had to put L by 2 cos theta. So the torque of that rod was L by 2 cos theta, which is perpendicular distance, into the weight of the rod, which is, okay, weight of the rod over here. I will solve RHS later on. So this will be L by 2 cos theta. Weight of the rod is density of rod into volume of rod into G, and L by 2 cos theta into density of rod is rho. Volume of the rod, if I assume the area of cross section to be area A, it will be small a into length because it's like a cylinder. Area into length is the volume. So A into L into G. So that is what I get in the LHS. See if everybody agrees till this point. Let me know guys. If this much is clear, then can I move ahead to the next part, the RHS part? Because only when you understand LHS, you will be able to understand RHS. Now, what is the buoyant force? Torque. The torque will be again perpendicular into buoyant force. What is the buoyant force? What is the distance? Let's talk about it. First of all, the buoyant force will act from the center of the displaced fluid. Observe this carefully. Observe this carefully. This much part is the displaced fluid. This much part is basically the displaced fluid. If you talk about the displaced fluid's center of mass, it will be somewhere here. This is where the center of buoyancy will be. This is where the center of buoyancy will be. So strictly speaking, the buoyant force is going to act from here. Yep, this is where the buoyant force is going to act from. Now the problem is that distance where the buoyant force acts, I do not know that. How do I find this out? Think again. I know what to do. Observe. Okay, observe this carefully. Look at this triangle. Okay, over here. This is where the water surface is. So this is where the water surface is. This is the surface of water. We all know that the height which was given to be L by 2 is this one. If this angle is theta and this angle is also theta, because parallel sides, right? Parallel lines, this will be also theta. If this is L by 2, I know what is this length. What do you think this length will be? Think carefully. This theta is, L by 2 is opposite theta. So I think that will be L by 2 sine theta. Visualize this. Won't the hypotenuse, think what the hypotenuse will be? This hypotenuse will be L by 2 by sine theta. Because if you take sine theta here, sine theta will be opposite by hypotenuse. Swap the terms, you get exactly the trigonometric ratio. Now, the center of buoyancy is somewhere here. This is center of buoyancy. This is exactly the midpoint of hypotenuse. is the midpoint of the hypotenuse, because that's where the center of mass of the displaced fluid will be. So if the hypotenuse is L by 2 sine theta, how much is this length? How much is this length? Think about it. This length will be nothing but L by 2 by 2. So L by 2 by 2, and you have sine theta here, which is basically L by 4 sine theta. Everybody getting this? Everybody understanding this concept till here? Everything is geometry. If you are strong with trigonometry and geometry, you will get this. So to locate this point, we first found out this length. How did we find this length? By drawing a big triangle, and this is the height, which is L by 2. So this hypotenuse, by trigonometry, we got it L by 2 sine theta. Midpoint will be half of that. So L by 4 sine theta is this length. But I don't need that. I need this length, because for calculation of torque, I need this much part. So this is strictly speaking R perpendicular. And how much will R perpendicular be? R perpendicular will be this length's cos theta. So this much part's cos theta, that means it will be L by 4 sine theta's cos theta, because this is adjacent side over here. So into cos theta. See now if it makes sense. This much part was this length. Cos theta in this small right angle triangle is this perpendicular distance on the force. This is exactly this distance. What a brilliant question it is. So this torque will be the R perpendicular, okay, R perpendicular multiplied by the buoyant force. So the perpendicular will be L by 4 sine theta, and you have cos theta on the top. Now I will erase all of this because I have found the R perpendicular value. I don't need this anymore, so I'm just going to erase this. I'm just going to erase this much part, okay, into buoyant force. Buoyant force will be the volume submerged into rho of the liquid, okay, rho of the liquid into G. Now think this way, this is L cos theta by 4 sine theta, volume submerged of this much part. What is this much length? I think I just had got this, the length of this guy. How much was the length of this guy? It was just, this was L by 2 and this was sine theta. This is what the total length was. So actually speaking, the volume submerged, the volume which is submerged will be area into this length, which is L by 2 sine theta, and density of liquid is 2 rho, okay, 2 rho into G. Now if you try to cancel out, let's see, G goes, rho and this rho goes, length goes, cos theta goes, area goes, okay, one more length goes. Then we also have this 2 and this 2 going, this 2 with this 4, yep. Now I think it makes sense. And now see what is remaining over here, nothing is remaining. So 1 is equal to sine theta into sine theta, that is sine square theta, and we just had 1 2 over here, that's it, and this is 1. So from this you will get sine square theta is half, from this you will get sine theta is 1 by root 2. If sine theta is 1 by root 2, that means theta is how much? 45 degree. That's the answer. Just check this out, see if it makes sense. Okay, I hope this is clear. So lot of trigonometry out here. What and all happened? The rod was floating, so the torque by gravity is balanced by torque of buoyant force. Gravity acts from the center of the rod, buoyant force acts from the center of the submerged part. So the challenge was to find the center of the rod, which was over here. So from that we got this, and the center of buoyancy is somewhere here. We got it via trigonometry. That's it. Rest all is just solving. That's all. As simple as that. Okay, so you will get the answer as 45 degrees. Perfecto. Now it's also time to have a look at, how many of you have solve the homework questions, because I'm going to give you homework questions as well. So just going back to the previous video, fluid mechanics lecture 1. There we go. Perfecto. There we have. Very good Ishpreet, very good Lalitesh, Chandan, Saja, Ishika, Dakshin, Harita, very good, very good. Yes, the second question's answer, I'll put it up in the Telegram group. Very good IT aspirant, very good Gokulnath. Yes, Vivek, I'm going to put it up, don't worry about it. And thank you for the lovely comments and education. You're going to get the PDF as well. Okay, so let me show you the let me show you the homework questions which you have to solve. This is the first homework question. Put up the answer in the comment section below. This is your second homework question which you're going to put up in the comment section again, and I'm going to read out all the names next lecture. Now, it's also very important to realize that Vedantu has a very good opportunity for all of you if you are interested to join a course online. You might be considering many online options. You might be probably even fed up of offline options, or maybe you just want to give a try to the online space because you are getting used to staying at home and you don't want to travel. So let me tell you, there is a course which has just started for 11th standard students, exclusively those who are latecomers. This is a latecomer course, exactly, which will help you right from the beginning till the end, complete 11th standard syllabus, okay, in this limited time that you have. Apart from this, after your 11th standard portions are over, you will have the 12th standard portions which will be starting from the month of April or May, and then after that you are going to go full speed till the last, and once your portions are done, you will have revisions which are going to go on, mock tests till the last day, till the last exam, be it JEE Mains or JEE Advanced. So that is basically your pro subscription. And in this subscription, you not only get a dedicated batch. See, when you join a coaching, you get a batch, but you get over here, you get micro courses, additional courses. So let's say you want to prepare for KVPY, you don't have to join any other batch, or any other institute or any other special payment. It's all inclusive. Be it my courses, be it my special courses, be it KVPY courses, it's all there. And the best part is everything is in English, so you don't have to struggle with regards to the language, and you will get your mock tests, assignments, report cards, everything. Now there are 3 versions. I'll just show it to you where you can find it. So when you're watching the video, even in the previous video or the current video, in the description box, you will see avail all exciting Vedantu courses, JEE 2 years. So this is exactly what you should be looking for. This is a batch which has just started, complete revision, topic specific courses, and you get 3 versions right over here. Light will include everything what I told you. And it also includes 2 teacher model where there is another teacher solving all your doubts. Classic will give you doubt solving on the mobile app after the class, and plus will also give you, additional help with the mentors. Now, even the smallest version, the smallest package is hardly 1,350 rupees per month. That's negligible. I mean, consider compare the prices with other online or other offline institutes which charge you around 2 to 3 lakhs for 2 years. 1,350. I know it says 15 days, but when you join using my coupon code SHHPRO, you get more 15 days. So you can try it out for 1 month. And if you are happy, you can buy the entire thing. Only the remaining amount is what you need to pay. Even when you go for the highest package, it's just 2,700 with my coupon code SHHPRO. The advantage of using my coupon code is you not only get discount, but any problem happens, you can directly get in touch with me. So when you say try for 15 days or buy complete course, you can see the coupon code will be applied. You have already saved so much. You have so many options to pay. That's how you enroll in Vedantu. That's the only way you can enroll in Vedantu. There is no need to call anyone, or there is no need to visit any office or anything like that. Everything is online. That's it. So I would love to see all of you out here, and I hope you had a splendid session. Do not forget to join the Telegram channel, and thank you for liking the video, and thank you for hitting the subscribe and promoting our channel to all your friends. Bye bye Carol, bye bye Madhav, NV18, Subramanyam. Take care Harry Potter shots. Have a great time ahead. How many gaps will be there between mains and advanced? Well, depending on the exams, depending on the boards, everything will be calibrated accordingly. So it will be on the spot. Don't worry, you will be getting enough time for revision, preparation, and for studies. You have a flexible schedule that you can choose, calm killer. All right, take care. Bye bye. Bye bye. This was Shreyas here, your captain, and I was going live from Bangalore. Have a great time. Hasta la vista.